Assalamualaikum and greetings. My name is Nur Ashani binti Amdin. Matrix number is 75497. We'll be presenting about the principle of heat transfer in a smoke tube boiler and how the design facilitates this process for MHP 3053 Marine System Engineering course. The smoke tube boiler, sometimes called a fire tube boiler, it's a workhorse in marine and industrial application. It deceptively simplifies whose core function relies on maximizing the transfer of thermal energy from hot combustion gases to water, turning it into useful steam. In this video, I will explain the three primary modes of heat transfer at light radiation, which is radiation, convection, and conduction, and critically how the boiler's unique design, particularly its multi-pass system, is engineered to facilitate and optimize every single one of these processes for peak efficiency. Basically, steam generation is simply a controlled heat exchange process. Within the boiler, the three classic modes of heat transfer are working simultaneously. The journey begins in the furnace, where fuel is burned. First, radiation. This is the dominant mode inside the furnace. High temperature flame and hot gases radiate thermal energy directly to the relatively cool surfaces of the furnace walls and the main boiler shell. Since radiant heat transfer is proportional to the difference of the fourth power of absolute temperatures, this initial stage is incredibly rapid and efficient due to the extreme temperature differential. Secondly, is convection. After the initial radiation phase, the hot combustion gases, now called flue gases, travel into smoke tubes. Convection takes over here. Heat is transferred from the moving hot gas stream across a boundary layer to the inner surface of the tube wall. The faster the gas moves up to an optimal point and the greater the turbulence, the more effective this convective transfer becomes. Thirdly is the conduction. Conduction is a crucial intermediate step. Once the heat reaches the inner tube surface via convection, it must pass through the metal thickness of the tube wall itself by conduction. Since boiler tubes are typically made of high quality, high thermal conductivity steel and are kept thin, this process is usually least restrictive path in the overall heat transfer chain. The true brilliance of the smoke tube boiler lies in how its physical design is specifically engineered to exploit and maximize these three transfer modes. We are talking about maximizing the heat transfer area and optimizing the temperature gradient. Design element for number one is the smoke tubes. By placing hundreds of small diameter tubes within the main shell, the boiler achieves a massive surface area to volume ratio. This dramatically increases total area available for convective heat exchange. The smaller the tube diameter, the closer every gas molecule is to the heat absorbing surface, improving the effectiveness of convection. So for design element number two, which is the multi-pass system, this is perhaps the most critical design feature. Like hot flue gases don't just pass through one set of tubes, they are often directed through 2, 3 or even 4 distinct passes, sometimes changing direction via smoke boxes. Why? Well, it's to maintain a large temperature gradient. As the gases travel, they lose heat. If they only had one pass, the temperature difference between the gas and the water will drop quickly, making heat transfer inefficient. By forcing the gases to travel longer, convoluted paths, you ensure a more complete heat extraction with an exit to the stack. This maximizes the residence time of the heat within the boiler. Now for the last design element, number 3, is water circulation and boundary layers. On the water side, the heat transfer occurs through a process called nucleated boiling. The water surrounding tubes absorb the heat conducted through the tube wall. Effective natural water circulation within the shell is essential to prevent the formation of a static thin film boundary layer on the outer tube surface, which acts as an insulator and severely impedes heat flow. Proper water treatment is also vital to prevent scale, which acts as another layer of insulation. To maintain thermal efficiency, two operational aspects are paramount: soot blowing and blowdown. On the gas side, soot and ash deposit on the inner tube walls, creating an insulating layer that drastically reduces convection transfer. Regular soot blowing is necessary to keep the heat transfer coefficient high. So, to maintain peak thermal efficiency, two operational aspects are paramount: soot blowing and blowdown. On the gas side, soot and ash deposit on the inner tube walls, creating an insulating layer that drastically reduces convective transfer. Regular soot blowing is necessary to keep the transfer heat coefficient high. On the water side, as we discussed, scale from impurities is a killer for conduction. The process of blowdown, removing water from bottom of the shell, helps control the concentration of suspended and dissolved solids, preventing scale formation and ensuring the tubes remain thermally conductive. In summary, a highly efficient smoke tube boiler is a perfectly balanced system. Its design utilizes a high surface area achieved through numerous thin tubes and a multi-pass flow path to prolong contact time and maintain the driving force. The temperature gradient to ensure maximum heat is transferred from the products of combustion to the water. That's all from me. Thank you.